Alright, AP Chem, we are in the home stretch now. So this video is going to be a little bit long, so you want your packet and flip to the end of page 3, and we're going to go through this, I don't know, this big table, alright? Again, if you had Honors Chem last year, I think, well, if you had me for Honors Chem, we covered this, or 2 years ago. If you're in General Chem, you probably just did 2, 3s, and 4s, but probably not 5s and 6s. But anyways, we're going to go through this fairly quickly. So Vsepr only applies to atoms with a central atom. So, for instance, we might have this guy that's in the middle, and these two things are going to be surrounding it. So valence shell electron pair repulsion says these pairs of electrons that are covalently or shared between the central atom and the outside atoms are going to want to be as far apart as possible. So we can do something like that. So here's a pair of electrons, there's a pair of electrons, or a cloud of electrons. So in that first column, you're going to put two shared clouds, alright? We can't have one shared cloud, only one, and have somebody in the middle, okay? So you can't play, monkey in the middle with two people, just called catch, alright? So anyways, we have two shared clouds, 0 lone clouds, and those first two columns are always going to sum to the third column. And then underneath total clouds you might have geometry. There's only one type of geometry with two things around it, and that's going to be the same as the shape, and this shape is linear. Alright, so the atoms themselves make a linear shape. The bond angle, so what's the angle between the two bonds, it's going to be 180 degrees. And again, if you look at kind of just our hybrid cheat sheet, if I have two electron clouds, my hybridization is Sp. Alright, so that is that one. Alright, on the next one, if we have three things, so three pairs of electrons trying to maintain the furthest distance possible around them, or around a central atom in 3 dimensions, we're going to have something that looks like this. Alright, something like that. So, in that first row, we're going to have three shared clouds. Is it shared? 3 shared, 0 lone, and 3 plus 0 is 3. The geometry is going to match the first shape. So this geometry looks like a triangle, alright? But if we look at it from the side, it's flat. So the triangle's in the same plane. So this is called Trigonal Planar. Trigonal Planar. Alright, because everybody is in the same plane. And the next column, what's it called? Bond angle. Really straightforward. So the bond angle between all these, if 360 is a circle, you cut it in 3 spots, 120 degrees. And once again, our hybridization is Sp2. Alright? So for the next one, we could just do like this. Would be a simple way to do it. Okay, so take off one of these. Now I have 2 shared and 1 lone. Alright? I think we'll just go with that. So 2 shared and 1 lone. So this geometry is still trigonal planar. Okay, so if there's 3 things, 3 clouds, 3 bonding areas, whether they're bonding or lone, so I guess 3 areas of electrons, it's going to be trigonal planar. However, this shape is trigonal planar, but this shape is no longer trigonal planar. This is bent, because we kind of pretend this doesn't exist. All right, so we pretend this doesn't exist. The atoms themselves look bent. However, these electrons are there, so they are still repelling these pairs of electrons. So if these electrons weren't here, it would come up and be linear again. But the electrons themselves do not contribute to the shape. They contribute to the geometry, but not the shape. Alright, so in this row right here, we're going to have 2 bonding, 1 lone, 2 plus 1 is 3, and then down here, we're going to have bent shape, but still 120 bond angle, and once again, Sp2 hybridized. And what we're going to find out, AP has not been that picky about it, but this is actually going to be less than 120, because this, I don't think I have one, because these are not kind of stretched between 2 atoms, they kind of puff out, more like a, I don't know, like a bulb on a flower. So because they are not stretched this way, they kind of go this way, and they take up a little more volume, which pushes these down, so they kind of, these, because they're not straight and stretched between, they actually reduce this so it's less than 120, but AP's good with approximately 120. Alright, So now we're going to move to the 4s. And the 4s are going to look like this. So we're going to start with bonding in all directions. And it's not just 2 up, 2 down. Alright? If we were looking at this possibly 2-dimensionally, it looks like 2 up, 2 down. But when we spin this, it's no longer 2 up, 2 down. Alright? It's kind of almost like a tripod looking thing. So we have 4 bonding, no lone. Alright? The geometry and the shape for this are going to be tetrahedral. The bond angle between each one of these bonds is 109.5. And the hybridization again is Sp3. Alright. Good with that? So 4 bonding, no lone. Geometry tetrahedral, shape tetrahedral. Tetra means 4, and hedron just means shape, or sided shape. So if we were to connect these dots, we'd have 1 side, 2 side, 3 side, 4 side, so it's a 4-sided shape. If we take one of these off, alright, so now we have 3 bonding areas and 1 lone area up here. So 3, 1, 4. If I take this off just for shape purposes, okay, I still have a triangle, but it's no longer flat, okay. You can see it's a pyramid. So this is Trigonal Pyramidal. Bond angle is still 109.5, or approximately. It's a little bit less than 109.5. And the hybridization is still going to be Sp3. Alright, lastly, we can take another one of these off. Alright. And in this case, we have 2 bonding, 2 lone. 2 plus 2 is 4. And we're back to a shape we've seen before. Again, if we ignore these lone pairs because they don't really exist when it comes to the shape, we have bent shape again. And again, quite a bit less than 109.5. This is actually closer to 104. And whatever, hybridization is still Sp3, and bond angle still 109.5. Alright, so 5. This is where it starts getting pretty fun. Alright. Alright, so if we want to arrange 5 things around a central atom, kind of look right now, kind of think North Pole, South Pole, and then we're going to have 3 in the equator. So it's kind of like a trigonal planar and a linear all mashed together. Alright? So if we start on that first row, 5 bonding areas, no lone areas, 5 plus 0 is 5. The geometry of this and the shape of this are going to be trigonal bipyramidal. So we basically have a pyramid on the top, and we have a pyramid on the bottom. So trigonal bipyramidal, because we have 2 pyramids. Bond angles, there's several that can happen. They can either be 180 from north to south pole, they can be 120 right between our equators, and they can also be 90 between north pole and equator. So several different bond angles that apply, and some more than others. I would say in this particular instance we'd have 90 and 120. Alright, but the bond angle between north and south isn't going to be that prevalent necessarily. Hybridization goes by the same rules. They don't test you on the AP with hybridization when we go to d orbitals, but this would be Sp3d. In the last several years there's been quite a bit of research saying that it doesn't really exist when we start having d's, hybrid orbitals don't. So anyways, it's not tested just because it's chemists across the board can't agree on it. Alright, so if I take one of these off, the question really becomes, is it better to take a North Pole off or an equator off? So if I take a North Pole off, notice these are still 90 in 3 ways and 120 in 3 ways. Alright, if I take this guy off, I've got 90 in 2 ways, 120 in 1 way, and then I have like 240. So it's actually better to take them off the equator. So in that second row, we're going to have 5 bonding, 1 lone. 5 plus 1 is 5. In this shape, this is where it was just like late Friday afternoon in the chemistry lab as they're naming stuff, and you got these trigonal pyramidal and trigonal bipyramidal, and someone's like, hey, you should put it on its side, look, it's a seesaw. So this is actually called seesaw or teeter-totter, all right, because it actually looks like a seesaw or a teeter-totter. And once again, bond angles are going to stay the same, and hybridization will stay the same. So if you take another one off, okay, so we have 3 bonding, 2 lone. And I don't know if it's the same Friday, different Friday. What was this one called? This is called T-shaped, because what's left, it looks like a T. So T-shaped, and once again, bond angle and hybridization, same. If we can lose one more, if we do lose one more, we've got this. So this would be 2 bonding, 3 lone. And you can see here this is definitely a 180 bond angle. All right, so it doesn't apply every time, but it applies in this instance for sure. So if we have 2 bonding, 3 lone, the shape is linear. It's still Sp3d dehybridized, and bond angle in this particular instance would only be 180. Just like if we put this one on, it would be 180 and 90. So you just kind of have to play it by ear. There's several bond angles possible with the shape, and you just have to kind of have the shape in your mind, have it drawn out, and be able to tell what you're drawing when you draw your Lewis structure, whether you can see it on the paper or see it in your mind. All right. So last one is these one with 6 areas, and there's only 3 of them, so it's actually a little bit easier. And we're just going to have like North Pole, South Pole, East, West. Turn it one more direction, East, West again. So it kind of looks like a kind of like a Rubik's cube, planes of a Rubik's cube, something kind of like that. Okay. So 6 bonding, no lone. This geometry and the shape are octahedral. So I have 1, 2, 3, 4, 5, 6, 7, 8 sides, so octahedral. Bond angles in this particular one are going to be 90, but it can't have 90 and 180. All right, we'll see that in a second. And hybridization Sp3d2. All right, so it doesn't matter which one of these I take off. I can take one of them off because they're all equally, they were all 90 degrees from each other beforehand. So again, pretend this doesn't exist. Well, actually, we can do our 5 bonding, 1 lone. So pretend this doesn't exist. So it looks like a pyramid again, if we were to connect the white balls. But now, from the top, it's no longer a triangle, it's a square. So this is a square pyramid or square pyramidal. And bond angle, again, we're going to have 180 and 90 this time. And hybridization stays the same. And then the last shape would be from the opposite side. All right. So this would be 4 bonding, 2 lone. Geometry is still octahedral, but our shape is now going to be square planar. All right. So it looks like a square from one side, and we rotate it 90 degrees. We can see that all the elements are in the same plane. All the atoms are. All right. So hybridization is still Sp3d2, and bond angles in this case 90 again between our equators and 180 kind of across our poles. So that is Vsepr really, really, really quickly. It really comes with practice, and you'll have a chance to practice via the homeworks and stuff like that. So anyways, that is it for this podcast.